Hello, welcome to this video on the independent sample t-test. So you'll see here I've got the formula for the independent sample t-test, and at the top of the formula we simply have the difference between the two group means. At the bottom of the formula you might notice that we have the standard error of the mean for group 1 and the standard error of the mean for group 2. So quite simply, the bottom part of the formula just reflects a type of average standard error of the mean for the groups. It's often described as the signal divided by the noise. In this instance, the difference in means is the signal, and the type of average standard error is considered the noise. The larger the signal and the smaller the noise, the larger the t-value that we obtain from our analysis. All right, so as you might know, when we report our results from our independent sample t-test, we report a t-value, as you can see here, but we also report a p-value. So the purpose of this video is to try and take you from the t-value to the p-value. But before we do that, we need to imagine a type of scenario. Imagine you're working in a research unit and you have a little bit of funding to do your research. You're able to test the IQ of 15 random males and 15 random females. And this is the focus of your research. Now, before you go into the field and conduct this research, you can actually do some early work on what might be the possible outcomes of this research, given the assumption that there's no difference in the population between male and female IQ. Male and female IQ average is 100, and the standard deviation for both groups is 100. So first of all, we make that assumption. Once we make that assumption, we can move to connecting T to P. All right, so imagine our staff, your analysts are out in the field at the moment and you have nothing to do. You know that you're going to have 15 males IQ estimates and 15 female IQ estimates from a random sample. You know that for a fact. So you're here in your lab wondering what to do. So you go ahead and you make that assumption and you carry out some analysis yourself on that population to develop a distribution of potential outcomes. So let's move to RStudio now to work on that. Now, inside RStudio, you will have the simulation set up, hopefully. As I said, we're having 15 males and 15 females. Let's call sample 1 the females and sample 2 the males. We set the population in the software to have a mean of 100 and a standard deviation of 15. Let's just run this once and see what type of output we get. So we're imagining a population of males and females with exactly the same IQ. We take a random sample of males, a random sample of females, run the t-test on those outputs, and see what we get. Okay, so we get a t-value of 1.12. So in this case, the average of the females must have been higher than the average of the males because it's a positive value. Okay, let's try and run it. Let's do it 10 times and see what we get. Okay, first one is positive, as before, positive again. Then we get a negative value. Positive, slightly positive, negative. So we're getting a mix here, a mix of results based on that random sample of 15 males and 15 females. Sometimes the females have a higher IQ, sometimes the males have a higher IQ. All right, so we can graph those results. You can see those results here. We have 10 statistics, 10 t-values, and they're around the 0 mark. Let's do 300 now from that known population distribution. Well, we should be looking at the distribution emerge. So we can see a type of pattern emerging. Most of the results center around 0, as we would expect, because that's true of the population. Of course, some of the results are nearer to the tails. We can see this distribution developing. And there we have it, starting to look like a bit of a bell. Let's move to 1000 and watch that develop. You can speed this up if you like. So what we would expect would be a type of more smooth curve in this case. Now, what type of distribution are we approaching in this case? Is it a normal distribution? In fact, it is not. It is called a t-distribution, which is slightly different. The tails are a little bit fatter in this case. So we can see this profile of potential outcomes, given the assumption that there's no difference in the population, emerge. Okay, shouldn't be too much longer. This is 1,000 replications. As I said, you can fast forward. So we're starting to approach a type of smooth distribution, but it's still a little bit disjointed. Okay, so there we have it. That's 1,000 replications. It takes some time to do it graphically like that. So let's do 200,000 replications this time, but without animation. And we can plot the results. can see your computer working down here. So this is 200,000 replications, and we'll come up with a distribution at the end. Again, you can fast forward it if you like. Just remember that right at this moment, our analysts are out in the field doing some IQ testing, and they haven't got the results yet, but the results are coming. What we're doing here is just doing some preparations for them to come and give us the results so that we can compare their results, the observed results, to our possible results given our assumption. And we're running the tests 200,000 times in this case. Maybe I need a new computer. I'll have to talk to my wife. Oh, it's done. Okay, fantastic. All right, so here we have the distribution of, the t-distribution of possible results. Now, you can see that I've put in the 95% confidence intervals. This is the upper 95% confidence interval. This is the lower 95% confidence interval. So the area under the blue represents 95% of all possible outcomes, given the assumption that the means in the population are the same. So there's 95% across here. That means we have these 2.5% red tails. We can see the lower and upper demarcation marks or type of thresholds. And I want you to think about what they might mean. So we have about 2.5% here to the right-hand side of the tail and 2.5% to the left-hand side of that tail. So this is the profile of potential outcomes of our research, given the assumption that there's no difference in the populations between IQ of male and females. All right. So we can imagine now that our analysts are coming back from the field, and we have results, a series of numbers for males and a series of numbers for females, 15 each. And the analyst runs the t-statistic, and they get a result in at 2.4. So the result is 2.4, around about here. Did I say positive 2.4 or negative 2.4? The result is 2.4. So that means that the female sample had a higher IQ than the male sample because the result is positive. So the result is 2.4. Let's put in 2.4. That is the result. That is the observed result. We also have to put that in at the other side as well. 2.4 here. So 2.4 is the t-value. What is the p-value? The p-value is officially 0.02. That means that if we were to shade in these small tail part areas here as partitioned from 2.4 and above, and we shaded in this other area here as partitioned by negative 2.4. These shaded areas, we can imagine we're shading them black. These shaded areas would constitute 2% of the total area under the graph. And 2% is the same as 0.02. So the p-value associated with the t-value of 2.4 is 0.02 in this case, for this sample situation, which is 15 from each group, but the total is 30. So the degrees of freedom is simply 28. Now, I hope that is helpful. It's the size of the tails as partitioned by the actual observed value, which gives us our t-value. And if our p-value is under this 95 or over this 95% confidence interval or below this 95% confidence interval, we can consider our results statistically significant. That means we can pretty much generalize to the population with some certainty that there are meaningful differences between the two groups in the population. Now, let's just imagine a one-tailed distribution. This is a two-tailed distribution, and it can be a little bit confusing. But imagine we had a one-tailed distribution. This would mean that the results could only be positive. So in this case, we could just tinker with the formula and put in the absolute values here. So this is always positive. We can draw the graph again with these absolute values. And we can just run that, get a result. So this is the same graph, but essentially we've folded one tail onto the other. And we get pretty much the same picture. This here represents 5% now of the total area under the graph because it's not split into two. Now, our actual observed result was 2.4, and that is here. So it's the area here. This area would constitute 2% of the total area under the graph. So our p-value is 0.02. We can also put in that threshold value here between these 2 points. All right, so I hope that helps. If you have any questions, you can put them in the video. Thank you for sharing. Thank you for listening. Bye-bye.